Okay. Welcome everybody to this week's Green Bank Observatory Community Zoom. I'm Jim Jackson, the director here. Not much to report other than some good news. The COVID restrictions have lifted. They're a little bit back now, but we are still able to open our visitor center, our science center here at Green Bank. So we will be opening that, have opened that. So that's good to have people on campus again. We're hosting school groups. So it feels like there's some activity on the campus again. So it's good to see some students and visitors about. Just a quick update on AAS. We will be attending the summer meeting in AAS. A few of us will be. I will be there. So if you are there, please make every effort to say hello and give me an earful about your opinions and wishes for the observatory. Look forward to that. The COVID situation is a bit fluid. It depends on the local conditions and the local case rates. 2 weeks ago we were green. This week we're now red, so masks are required, but it's a very fluid situation and it really does depend on somewhat small number statistics here in Pocahontas County. So we will find out every Friday about what the status for the following week will be. So, but we still are accepting visitors. Just have to follow the COVID protocols. All right, that's all I have for the observatory update. I'm going to hand it off to Dave Freyer, who will introduce today's speaker.
Hi, everybody. Thank you for joining. It's our pleasure to welcome Patrick to give one of our community Zooms today. He's a real world-renowned radar expert, and he has recently just joined the NRAO and GBO as our radar division lead. So Patrick, go ahead and take it away. Oh, if you have questions, I always forget to say this, put them in the Q&A and we can address them after the presentation. Thank you. We can see your first slide, Patrick.
Okay. I'm hoping to get rid of being able to see myself and everyone else in the chat, but I can't see it. Sorry, 1 second. Just hide that real quick. Okay, that's better. So as Dave said, my name's Patrick Taylor. I am the NRAO GBO Radar Division Head. I just started here in December. Prior to working here, I spent the vast majority of my career down at Arecibo Observatory working on the planetary radar down there. But what I want to talk about today is sort of the past, present, and future of planetary radar with the Green Bank telescope. So first of all, how does radar work? For those of you that may not be very familiar with this is active radio observing. So what we would do is we start with commercial or generator power. We amplify our signal or waveform with klystrons, which are vacuum tube amplifiers or solid state devices, and transmit that signal out into space. So we could transmit unmodulated signals, so essentially a continuous tone into space, or we can modulate that signal in a known way and use that to gain extra information. And this is typically done in circular polarization. We transmit in one circular polarization, and then we receive the echoes in both circular polarizations, the same and the opposite sense of what we transmitted. So unfortunately, I can't see my own cursor, which is unfortunate. So if you look at the diagram on the left, essentially the idea is the red arrows are the transmitted signal. In this case from Arecibo, the transmitter was up in the Gregorian dome. The signal was transmitted out through the Gregorian tertiary and secondary and down to the primary reflector and out into space, where it then bounced off our target, whether it's an asteroid, the moon, or another planet, or whatever our target may be. And then the signal comes back as the blue lines reflects off the primary reflector and is collected by the receiver. So in this case, where the transmitter and the receiver are in the same place, you would have to transmit for roughly the time it took the light to go out and back to the telescope. And then you would swap out the transmitter and put the receiver in the focus to record the echo. And one important thing about radar is because you're sending a signal out and then having it come back, you're losing 1/r², so inverse square law, in both directions. So our signal strength is going as distance to the 4th power. So that means it's really hard to use radar on things that are far away and very small. And to compensate for that, you want to use the largest telescopes you can and transmit as much power as possible. And the really important thing about radar is since we control the signal that went out, anything that changes about that signal when it returns to us is telling us about the properties of the target. So what are we actually measuring? Really, we just measure times and frequencies, but we do it really, really well. So if we can measure the time delay it takes for that echo to go out and come back, that's telling us the distance to the object. And we can measure that distance to sort of the 1 part in 10 or 100 million. And we can do similarly in velocity or in terms of frequency or Doppler shift. So by measuring the frequency that the echo comes back out at, comes back to us at, we can determine the velocity and how things are moving on the target that we're looking at. So if we think about this in terms of asteroids and small bodies, if you can measure that time delay and that Doppler shift really, really well, it's telling you how far away something is and how fast it's moving. And that's exactly what you need to determine the orbit of an object. So when you have a very new object who has a very uncertain orbit, if you can get radar on it, it's incredibly powerful for really crushing down the uncertainties on the orbit and helping you be able to figure out where that object's going to be in the future. If you can go further, if you go further than that, the first step is sort of the bulk distance and the bulk velocity of the object and how it's moving. But if you can then resolve that distance to get a depth of an echo, it tells you something about the size and the shape of the target. If you do the same thing in velocity in terms of the echo is being dispersed across different frequencies, that tells you something about how the object is moving in terms of its rotation, not just its translational velocity. And then we can also learn about the scattering properties, whether something appears radar bright or dark is telling you something about how it can reflect the signal, how your transmitted signal is comes back polarized or depolarized, tells you things about the roughness and the composition of the target that it bounced off of. And when you put all this together, it's properties that you really want to know for planetary science, planetary defense, and space situational awareness. So I'm going to be showing a few radar images, which we often call delayed Doppler images or range Doppler maps. So essentially what this is taking a 3-dimensional object and smushing it down into 2 dimensions. So if you look at the diagram on the left, imagine that you're holding a ball in front of you and you're the transmitter, and that diagram is the ball you're holding in front of you. Essentially, the green dot in the middle, that's sort of your sub-observer point. And the circles, the concentric circles around it are all the points that are the same distance away from you. Then the vertical lines on there are all the positions that have the same Doppler shift. So if you imagine this thing is rotating with the left side towards you, so the blue points are blue shifted, and the right side is moving away from you as it rotates, so the red dots are red shifted. The vertical lines are telling you which points have the same Doppler shift. And essentially what the radar does is it takes that 3-dimensional shape and it smushes essentially the dimension in the plane of the screen. So imagine taking that ball and just smushing it vertically. Then the radar image is what you see if you look at the screen. So the mapping is that the subradar point, the green dot, translates to the green dot on the right in the Doppler, delay Doppler image. And the red and blue dots also translate to each other. So essentially you've taken a 3-dimensional object and smushed it down into 2 dimensions, where the dimensions are range vertically. So that's time delay or range or distance from the observer, however you like to think of it. And the horizontal dimension is not quite spatial, it's the Doppler shift or the velocity of the object. So the spread horizontally is telling you about the rotational velocity of the points on the object. So that's the primer to get into actual radar imaging. So I wanted to say a bit about the history of planetary radar with the GBT. GBT has participated in planetary radar not as a transmitter, but as a receiver, essentially since its inauguration. I know there were observations in roughly March of 2001. I don't know if they were the first radar done with GBT receiving or not, but that just gives you an idea. GBT has been involved in this sort of work for over 20 years. But since it didn't have a transmitter, it always acted as a receiver. And some of the things it has done include understanding the interior properties of Mercury. In the top right there, you have the cover of Science magazine back in 2007. This was for work done by Jean-Luc Margot and colleagues who used very accurate radar measurements to understand the spin state of Mercury and use this to constrain that it has a molten core rather than a solid core. And that continued observations of Mercury have helped them understand the moment of inertia of the core and its size, which has been very helpful to figure out. And similar observations have been done with Venus, also by Jean-Luc Margot, to understand the length of the day on Venus. Because as you know, Venus has a very thick atmosphere and you can't easily measure what is happening on the surface. Radar is able to pierce through the atmosphere of Venus, and you can use radar to measure the rotation state of the planet itself, the solid planet. And this has been a long-term project to understand the length of the day on Venus and whether it actually is changing with time. Then another common thing that GBT has participated in is observations of the moon, an example of which is the background here, done by Bruce Campbell at the Smithsonian Institute. This was a radar image from Arecibo transmitting and Green Bank receiving. And the reason that Green Bank was commonly used for observations of the moon is the moon is so close to us that it's essentially impossible to do observations where you both transmit and receive at the same site. So in the case of Arecibo, it takes time to switch from transmit to receive, but the echo from the moon comes back in about 2.5 seconds. And if you can't switch to receive in under 2.5 seconds, you simply can't observe the moon with radar. So the way you get around that is you have someone else do the receiving for you. So why not use the biggest telescope you can and Green Bank, and you have Arecibo do the transmitting to the moon and Green Bank receives it. And you get an image like this in the background. And you may notice that it kind of looks like watermelon stripes. There's the bright part in the middle, and then there's dark lines on either side of the bright area, and then it gets bright again. This is because you're literally seeing the beam pattern of the telescope. So those are the first nulls, or the dark spots, the dark stripes you're seeing there. So the main thing I've worked on is using Green Bank with asteroids. And there's several reasons that you would use Green Bank. One is it obviously has a large receiving aperture. So there's, besides Arecibo, the other main transmitting station is a 70-meter antenna, as in part of the Deep Space Network in California. So it's a 70-meter antenna, but if they can use a 100-meter antenna, as in Green Bank, it's a much larger receiving aperture, and they can boost their signal to noise in their images. So that's one reason to use Green Bank. The other, another I've already mentioned, is for things that are very close, like the moon you can use green bank as the receiver, so you don't have to keep switching between transmit and receive. This also applies to asteroids. If an asteroid comes within a few lunar distances or even closer to the Earth than the moon is, then obviously you would want to bring in green bank to receive those echoes for you. And the other thing I hadn't touched on yet was you can get finer frequency resolution. So in these images, your frequency resolution is dependent on essentially your integration time. So if you have to keep breaking up your integration time by turning on the transmitter and then turning it off and receiving and turning the transmitter on again, that limits your frequency resolution. But if you just transmit continuously from one site and receive continuously at green bank, you can essentially make your integration time whatever you want, which means you can make your frequency resolution essentially as fine as you want. And that'll be important in some of the next slides. So I'm going to go through some of the best and brightest radar images we've gotten using green bank. This is an object called 2003 SD220. The top row of images there are done at X band, so 8.56 gigahertz or 3.5 centimeters. So Goldstone in California, the 70 meter, would transmit and green bank did the receiving. And you get these images where, if you note the resolution there, are 3.75 meters per pixel vertically. And horizontally, the frequency resolution is 0.0025 hertz. And these images are possible because we were doing this bistatic mode where we transmitted continuously and received continuously at green bank. And you can see incredible detail, especially in the top right image there. You can see bright spots that could be boulders on the surface. You see ridges, concavities, and such. The bottom row there are similar images done with green bank, with Arecibo transmitting to green bank at S band. So this is 2.38 gigahertz and 12.6 centimeter transmission being received by green bank. And you can see the same object, but in different orientations than seen before. And similar, really incredible detail, especially in the bottom right there. And once again, the resolution here is just incredibly fine, 7.5 meters per pixel and about 1 millihertz in frequency resolution. So this is an interesting object. It's extremely elongated. It's more than 2 kilometers long, but it's kind of shaped like a sweet potato. And it's got an extremely long rotation period. It rotates once every about 2 weeks. So each of these snapshots is from a different day because it rotated so slowly. There was essentially no change during the observations each day. This was another really great example of an asteroid result using Goldstone and green bank. This is 2004 BL86 from 2015. This was done as partly a test of the radar backend at green bank in 2015. And it was also done to test observations with the DSS-13 transmitter, which is a 34 meter telescope at Goldstone working at C-band. So this is like 7.2 gigahertz and 4 centimeters or so. And you can see incredible detail in this asteroid. You can see it's mostly rounded, but you can see very clear ridges and protrusions and sort of linear features and other bright features. The object there is about 350 meters in diameter. And the really important thing here is you see that bright object zooming along from the center of the screen up to the top. That is a moon. So this object has its own little moon that orbits it. That bright speck there is about 70 meters in diameter. It's likely tidally locked to the primary bigger asteroid, just like Earth's moon is tidally locked to Earth. So this is a really powerful thing that radar can do, is it can quickly identify binary objects, so objects with moons, because it can just unambiguously show you that there's 2 separate objects in this picture. I'm going to show this one because this one's near and dear to my heart. This is 2017 YE5. These are observations from Goldstone. They were looking at it monostatically, so they were both transmitting and receiving. And they looked at it on 3 dates, and they could see that it looked like 2 objects, but they couldn't quite tell if the objects were separate or not. So one way to try and figure out what is going on here is to get even better frequency resolution to try and separate them horizontally. So they got Greenbank to be the receiver, and well, these are actually Arecibo. So Arecibo got Greenbank to be the receiver, and you can see very clearly these are now unambiguously 2 objects, and they're well separated, and they orbit each other. So they're, instead of being one large asteroid and one tiny asteroid, these are 2 similar size asteroids that are orbiting around each other. And we looked at it on one day, and we thought, these are great images. Let's get another day of it to see what it looks like. And we came back the next day, and we got this image. And if I scroll back and forth a couple times, it looked the exact same. So what that told us is that these 2 are orbiting each other, but they orbit each other in almost exactly 24 hours. So we, we ended up seeing pretty much the same image on 2 different days. But this confirmed that they were 2 separate objects rather than 2 objects that were stuck together or in contact with each other. So that's sort of some of the history of using Greenbank with planetary radar. But so starting around 2015 or so, there was a workshop held at Greenbank about the future of planetary science at radio wavelengths. And I think that's really where the consideration began about trying to put a transmitter on Greenbank rather than only receiving. So at that time, you had Arecibo and Goldstone as transmitters. Arecibo had 2 different transmitters, one at P band, so 430 megahertz or 70 centimeters, that was mainly used for atmospheric or ionospheric studies and sometimes the moon. And it also had the S-band transmitters, what we mainly used for planets and the asteroids, comets, things like that. Goldstone, meanwhile, had higher frequencies, the C-band transmitter on the 34 meter that I mentioned before, and the X-band transmitter on the 70 meter. So the logical thought at that time was, if we're going to put a transmitter on Greenbank, we should leverage its surface accuracy and go as high as we can with a transmitter in K-band somewhere. So looking at sort of centimeter scale wavelengths, sort of in 1335 gigahertz kind of range. And the idea here was it would expand our multi-wavelength capabilities and also provide redundancy, because it was not uncommon for Arecibo or Goldstone to have maintenance that needed to be done that would take them out of commission for weeks or even months, depending what the issue was. So having another transmitting facility would give us some redundancy and make sure that there weren't times that we had no radar capabilities, which has happened in the past. So another thing that comes to mind for why we would want more radar facilities is NASA has been tasked with discovering, tracking, and characterizing 90% of near-Earth asteroids bigger than 140 meters. And this was originally tasked in 2005, and to date, it's only about 30% complete. So to address that, in the near future, we have LSST, the Vera Rubin telescope, will be coming online, which will discover just an incredible number of small bodies and near-Earth asteroids. And we're also trying to get the near-Earth object surveillance mission launched, which is an infrared telescope that will be dedicated to trying to discover and characterize near-Earth asteroids. But when you have these very impressive missions discovering things, you also need to have the capability to track and characterize the things that are discovered. And that's something radars can very strongly help out with. So if we have more objects being discovered, we're going to want other facilities that can do the tracking and characterization for them. And Greenbank could help out with that by adding a transmitter. And then in the last few years, since this project has really gotten going, we lost Arecibo. So now there's even a larger void that needs to be filled in terms of planetary radar capabilities. So in the last couple years, this is putting a transmitter on Green Bank has actually become a real thing. So NRAO, Green Bank, and partners with Raytheon Technologies have already put a prototype transmitter on the GBT. It was put at the prime focus, so on the right there at the top of the structure of the GBT on the prime focus boom, they mounted one of these prime focus housings that contained a small transmitter. And the transmitter's there on the left. It's about 700 watts that could be transmitted. And it was mounted up there and used in a couple of observations in late 2020 and early 2021. And these are summarized in a paper by Steve Wilkinson that was recently published in the Microwave Journal. So I encourage you to check that out. So one of the tests they wanted to do was obviously what's big and bright and nearby, that's the moon. So one of the first tests was looking at the Apollo 15 landing site on the moon, which is with this, this zoom in here is showing. And this is an example of a range and Doppler map that was received with the prototype transmitter. So the transmission was done from Green Bank. It was received with the VLBA. In this case, we're showing a radar image from the Pytown VLBA antenna. And you've got range increasing from the top down, and the horizontal dimension is frequency or range rate or frequency or Doppler shift, however you want to think about it. The curvature of the moon in this image is not realistic. It's due to the resolution and the shape of the image. This isn't physically what the moon necessarily looks like, but you can see an incredible variation in relief. And you can take these radar images and then reproject them into more physical space, essentially doing synthetic aperture radar. And you can get something like this. This is a zoom in of the Apollo 15 landing site. The Apollo 15 landing site is sort of in the bottom left-hand part of this image. And this image here has 5-meter resolution. So the pixels in here are each 5 by 5 meters or so. The crater at the top center is about 6 kilometers wide. And it's called Hadley C. The sort of ditch through here is called the Hadley Rill, and the Apollo 15 landing site was just below the rill in the bottom left. And another image that was done as a test was Tycho crater on the moon. Again, this is a 5 by 5 meter resolution of Tycho crater. And this is the highest resolution ground-based image ever taken of the moon. So this is really incredible, especially when you consider this is just a 700 watt transmitter and just one receiving antenna with the VLBA. But yeah, incredible detail in these images. And on top of doing the moon, there happened to be a good-sized asteroid flying by Earth called 2001 FO32. It's large and made a close flyby, so it's considered potentially hazardous, although it's not a threat to Earth at all. It's just a definition of its characteristics. Sort of several hundred meters or kilometer scale asteroid. It flew by the Earth at about 5 lunar distances, so 5 or 6 times further away from Earth than the moon's orbit. And in the bottom left, it's not the prettiest image ever made, but this is a echo power spectrum of 2001 FO32. So the spike there just to the right of 0 is a successful detection of the asteroid. So this was the first asteroid detected with a transmitter on the GBT. So GBT was transmitting at about 600 watts, and the receiver was the St. Croix VLBA antenna. So the next step here is to try and make a high power transmitter system for the GBT. So really our goal is to make a powerful next generation radar system for planetary science and defense. And the current status is based on the prototype data I just showed. NRAO, GBO, and Raytheon have received funding from the NSF with a mid-scale research initiative award for the next year or so to do design and concept studies for a high power radar. So we're working on designs and concepts to be able to put roughly a 500 kilowatt output power transmitter at K-band, somewhere between 13 and 35 gigahertz, and doing this with a solid state transmitter architecture. So this is not using klystrons like Arecibo and Goldstone use. This is using a different solid state technology. And right now we're sort of working through the ideas of what may and may not work for a system like this on the GBT. So we need to balance science requirements along with technical practicality. And this includes thinking about the physical size of the transmitter system, its weight, how much power you need to put in and send up the GBT to power it, how efficiently you can get that power into space, what it takes to cool the radar system, the optics of it to make sure you're not interfering with other things on the GBT or degrading your beam, what structural modifications it would take to put such a system on the GBT, and also how you protect the receivers if you start blasting 0.5 megawatt past very sensitive receivers. How do you keep them safe? So we've received pretty broad community support for this sort of task. We wrote a lot of community white papers for the astronomy and the planetary science decadals, supporting not just Green Bank as a whole, but the idea of putting a transmitter on it. We had papers describing the science that you could do with different radar systems at the different sites, trying to defend the use of single dish radio astronomy facilities for radar. So of course, including Green Bank. And so we've put those into the decadal surveys. We also get community support through things like the NASA Small Bodies Assessment Group. They recently had a meeting in January, and among their findings that they're going to send to NASA is support for planetary radar facilities. And I've highlighted there that the current efforts to install a planetary radar system on GBT are an example of how NASA can work with other agencies like the NSF to build up planetary radar capabilities. So to sum up here, GBT has been a steady contributor to the planetary radar as a receiver for more than 20 years. And now in the last few years, we now have been using a transmitter on the GBT. So the prototype transmitter was only 700 watts, but it provided very compelling results. So like for that asteroid, you're detecting an asteroid that's 5 times further away than the moon with output power that's less than your microwave. So that's pretty impressive. So imagine if you could be sending out 1,000 times more power and have the full VLBA or eventually the next generation VLA doing your receiving for you. So currently we're working on the design concepts, trade studies, requirements, definition, all that fun stuff. So we can start looking into actually building a high power system on the GBT. And as we do that, we're definitely open to community input and feedback on requirements and desires and such. And we're hoping if COVID ever sort of stops messing with us and lets us go back to normal, we would love to have an in-person workshop perhaps this summer to discuss the system even more. So if you have questions, comments, torches, pitchforks, suggestions, please feel free to contact me or project scientist Flora Paganelli with your thoughts, and I'm happy to take questions.
Thank you very much, Patrick. We have some questions here. Well, I'm just going to jump in with the question because out of curiosity, have the numbers been worked out to see how far like with this new GBT radar system as a transmitter and then maybe the future ngVLA as a receiving station, how far out could you detect a planet killer, like a 10-kilometer size asteroid? Has somebody worked through those numbers?
So I carefully avoided putting any of that
curious.
in there. I mean, obviously, we would want this to be, as good and hopefully even better than what Arecibo could do. Having ngVLA would certainly be a huge step in doing that, just because of the sheer number and effective receiving aperture you'd have. So yeah, there's potential for this to expand, beyond what Arecibo could do, hunting for things at a few tenths of an AU rather than sort of a tenth an AU and under, would certainly be something very compelling to be able to do. Get as much warning time as possible.
Okay.
Yeah, there's just a lot of variables still in here that can make an order of magnitude change.
So even fuzzy by astronomer standards in terms of numbers. Okay, fair.
That's fair. That's essentially what we're trying to work out in the next year, is really fine tune those estimates.
Okay, there are a couple links on here that were provided in terms of illustrating the double binary asteroid. I will leave those links on there, and then John Luke presented another link. But in terms of questions, we have a question: does FAST have radar capabilities?
So no, they don't, because the way they have, at least the way they have built the cabin that houses their system, they certainly can't put at least a transmitter of the style of Arecibo. It's just not possible. They can't put that sort of weight into the cabin. And then you'd have to worry about how to power it and cool it as well, which would be pretty difficult. So no, I don't think there are plans to have transmitting capabilities at FAST, but they certainly could participate as a receiver in the same way that Green Bank did in the past, if you can get the right sky overlap between them and a transmitting station.
Okay, now we have a question from a potential future observer. What's the timeline for the 500 kilowatt transmitter at the GBT? When will it be ready for observations?
So obviously the big thing right now is, well, after we design it, of course, is getting something like that funding, which is certainly no easy task. It would be a big infrastructure project. I would estimate this is sort of a 5-year sort of project, and moving at the speed of government, who knows what that could sort of turn out to be.
Okay, another question related, complimenting you on your talk. A participant brought up the W-band possibilities using the Haystack Herzer transmitter. Your thoughts on this? You've shown what can be done with 700 watts.
So yeah, Haystack does have a W-band transmitter. I'm admittedly not very familiar with their system, but NREO certainly has things that can do W-band. So that's something that we could think about if there's a science that could be done receiving from Haystack.
Yeah, we have a W-band receiver. I'm not sure how our back end connect. Well, anyway, with W-band locally. Okay. Wow, lots of questions are coming in. Would it make sense someday to send a robotic RTG powered radio transmitter into space, perhaps to the asteroid belt, to transmit and modulate signals at targets from relatively short range for detection by the GBT? I'm trying to. Sorry.
I will admit I do not have a good answer, but certainly if there's ways that you can remove some of that 1/r² dependency by either having the receiver at the target or the transmitter at the target, that's certainly helpful. I don't have a good answer for that one right now.
That's fair. And another question, is there any effort to revive or build another Arecibo?
Well, there's certainly efforts. I know the team down in Arecibo is still there. They're still working. They're still doing good science and looking for ways to push forward ideas that will help rebuild the site so it can do more science now and then do cutting edge science in the future. What form that will take, that's still an open question. There's been various suggestions for a new big dish, or a big dish made of smaller dishes, or having several ngVLA style antenna in Arecibo. There's still a lot of ideas being kicked around. So yeah, there's always the possibility that something new will end up in Arecibo.
Okay, we had a question about the future, possibly using ALMA as a receiving station, since they're in a few years it'll have capability at 35 gigahertz, and they're still designing the specs for the new correlator. So you being an NRAO, I don't know if we go with the Ka band, whether ALMA would be interesting as a receive station.
I mean, if they have a receiver at the right frequency, I suppose anything's possible, and we certainly have people that could figure it out here at NRAO.
Okay. And then another question, are you still planning on only bistatic configurations, or are you considering monostatic for more distant targets with the GBT, I'm assuming?
There's been no real plan of doing monostatic with this system. Yeah, we've been thinking mainly of the bistatic idea, rather than having to switch between transmitting and receiving at one site.
Okay, and then a comment that came in about using ALMA with haystack at W band could be interesting with 8 gigahertz of bandwidth. Then they're talking about getting centimeter resolution. That's not necessarily a question. We have some more. Okay, there's discussion now in the chat with ALMA, the VLA can receive at K band as well. ALMA soon enough, VLA now, presuming the high-powered radar gets completed before the ngVLA. It's just a comment saying the VLA could be used as well. And then Flora's, okay. Flora provided a link for an update of ALMA at 35 gigahertz this afternoon. If interest, there's another webinar. So. Being advertised. Okay. I think if there are no other questions, we went through it. There's some interesting discussion going on in the Q&A, and your talk generated a lot of interest.
Dave, there was a question that came in the chat on being tidally locked. I'm not sure if Patrick touched on that.
No, okay, yeah, we could, yeah, okay. The question.
Quickly. Yeah, so I said that the moon of that asteroid is likely tidally locked. So by that, I mean that its rotation period and the orbital period about the larger asteroid are the same. So it would keep the same face towards the larger asteroid in the same way that the moon keeps the same face towards Earth. And we would expect that to happen through tidal damping, tidal interactions, the same way that the moon was spun down to be tidally locked to Earth.
And then maybe our last question, they're thanking you for your talk, but they're also saying, is the goal for this high-powered radar on the GBT, will it be a facility instrument in the future? Is that the goal?
I'm not sure what that means.
I think it
Does that
means
mean
be
open to the
open to
community?
general observers, basically, to use and propose to use.
Yes, I think so. I don't think this is a, I don't think it's meant to be secretive or anything.
Yeah, I think I got maybe there's more of a question yet on like it'd be open, maybe a general user instrument, not a insider instrument. So I would hope that we would pursue that. So okay, whoops. Oh, then there's comments with questions. Okay, people are using the QA to ask questions to each other. So I about a paper on the specs with the radar, haystack radar. So I think we can close off our webinar here with Patrick. Thank you very much for joining, and we'll look forward to the community coming to webinars, future webinars with the GBT. So we'll look for those advertisements. So thanks again, Patrick, for a great presentation.
And a quick reminder to everybody on the call, these recordings will be available on our website in the future, probably within a day or so. So thank you very much for coming.